Hi guys, hope everybody's having a good day today so far. Today we're going to talk about the geometry of constrained optimization. And so we'll start off with a constrained maximization problem. And in fact, everything we're going to do today is with maximization, but of course we know that minimization, we can just multiply our objective function by -1 and then maximize it so we can compare the conditions. So we're going to start off with probably the simplest kind of constrained maximization problem, and that's going to be where we have, I'm going to use P as the name of the problem, and that is to maximize a function f of x where x is in Rn, but I'm going to have n equals 2 to begin with. And this is going to be subject to one constraint. And so the constraint is going to be g of x equals some number b. And let's assume throughout today that this is going to be a strictly quasi-concave objective function. And we'll start off, as I said, with n equals 2. And I'm also going to start, so I'm in space, in 2 dimensions, and I'm starting with one constraint. And I'm actually going to start with the constraint being linear. So let's go over here, and we'll say we have just one constraint. And it's going to be a linear constraint. So let's first draw a typical linear constraint. It's going to be a straight line in space, in 2 dimensions. So it will look like this, let's say. And so this is going to be the set of all points in R2 such that g of x equals b. So this is the constraint. And so this says we have to be on the constraint. It's an equation constraint. And so I'm actually going to give this line the name h for reasons that may already be clear, but if not, I'll make them clear a little bit later. And we are going to be interested in the question here whether some given point is a solution to the problem. So let's say we want to know, is x hat, where x hat is some particular point, is x hat a solution of the problem P? That is it a maximizer of f subject to the constraint? So let's take the only reasonable candidate, of course, is going to have to be something that does satisfy the constraint. So let's start by taking an x hat like this, and let me use this color here, and we'll say this is x hat. And so it satisfies the constraint. It's on the line, and I want to know if it maximizes the function among all the possible points that do satisfy the constraint, that are on the line. Let's do a little more with the constraint before we put in our f here. Let's note that displacements or movements away from x hat, I'm going to call delta x, as we've done before. And so this is all the constraint, the line, could also be written as all of the delta x's, all the points, let's say, where the gradient of g dot delta x is 0. Well, I haven't drawn the gradient. I probably should have drawn the gradient before putting that in here. Let's draw the gradient here. So the gradient, we know, is a vector that is perpendicular. That's supposed to be perpendicular or orthogonal to the line. It looks like it kind of, I have a tendency to do that. So let me actually try to make that so it really is, it really is orthogonal here. Let's see if I can do that. That looks a little bit better. So that's going to be the gradient of g. So I know that the gradient of g is orthogonal to the set or line g of x equals b, and that means it could point this way. Of course, it could point this way too. It just depends on which way g is increasing. So this says g is increasing this way. And in fact, let's even point out that since it's a linear constraint, I could rewrite this, if I want, I could write it as a11 x1 plus not make that a11, make that just a. a1 x1 plus a2 x2 equals b, because g of x is a linear function. Let's get this out of here too and make that a little bit bigger. And so that is a typical linear expression, linear function. And let's note then that this is a1 delta x1 plus a2 delta x2 equals 0. It should be the same coefficients. The gradient of g, if it's a linear function, the gradient of g is just the vector of its coefficients, a1 and a2. So that gives us a pretty complete kind of story and details of the constraint. Let's see if I'm leaving out anything that I want here. Well, in a way, I guess I am. So let me put in here that this is also the place where delta x is the 0 vector in R2, right? So there's here delta x is 0, and if I move this way or this way, delta x becomes non-zero. When I say 0, I mean the 0 vector here, of course. Okay, so now let's put in our objective function. So if x hat is a maximum, if it is a solution to the problem, then we know from intermediate microeconomics probably, or first course maybe in calculus even, I don't know. We know that things are going to look like this. So the level curve of the function f that goes through x hat has to look like this. That is, it has to be a tangency. So let me actually write over here that the level curve all the points in the space for which f of x equals f of x hat, the level curve through x hat is this curve here, and it has this shape because it's strictly quasi-concave. F is strictly quasi-concave, and I notice this is getting a little bit fat here, so I'm going to change markers to make these a little finer. So now we have a tangency at x hat. In fact, let's even say tangent at x hat between the level curve of f and the constraint. And that means that the gradient of f looks like this. And actually, I could have it come all the way out here like that. The gradient f coincides in direction with the gradient of g. In fact, I say it coincides in direction. That's not quite true because the gradient of g could point this way. Gradient of g has to be orthogonal to the line, g of x equals b, but it could point this way, it could point this way. Either way, the gradient of f is equal to a multiple of the gradient of g. This way, if g points this way, well, then it's a negative multiple. And if they point in the same direction, then it's a positive multiple of g. In the picture here, lambda is bigger than 1 because gradient f is longer than gradient g, but could be shorter. So now let's just note the one more thing I want to just emphasize here is that being tangent at x hat, the level curve and the constraint being tangent at x hat is characterized, it seems, by the this relation between the gradients of the two functions, that the gradients are multiples of one another. Now, I want to see, so this is a situation where x hat is indeed a solution. It's clear that x hat maximizes f among the things, among the points on the constraint, because all the other points on the constraint are on lower level curves. And of course, this is partly coming from the quasi-concavity of f. So what I want to do now is I want to see what would this look like if gradient f was not equal to lambda times gradient g. Suppose that the two gradients didn't point in the same direction. Now I could do that by just moving my f around, rotating my f level curve around a little bit so that the gradient didn't point this way but pointed a different way. I could just erase this and do a new one, but I was going to do that, but I decided no, I think it would be a good idea to have both of the pictures here on the screen at the same time. So I'm going to redraw gradient. I'm going to redraw the constraint. And so again, this is the constraint where g of x equals b, where gradient g dot delta x is 0. This is x hat. So let's put that in again too. This is x hat, where delta x is the 0 vector. And let's also put in the gradient. I'm going to try to get it orthogonal. Okay, so there we have our gradient of g. I call this h, so I'm kind of reproducing that diagram. But I want to have now the gradient of f not pointing in exactly the same direction. So I'm going to have the gradient of f pointing a little bit this way, and that means that my function, the level curve of my function, has to look something like this. So this is now the level curve, all the x's, such that f of x equals f of x hat. And now notice that the gradient of f at x hat is, of course, orthogonal or perpendicular to the level curve at x hat. So that has to look like this. So this would be the gradient of f. And you can see that it is indeed not equal to the gradient, a multiple of the gradient of g. Now, why I'm writing lowercase g, I have no idea. But there we go. So unequal. So the difference between the two diagrams is just that I've changed my function f. So it's not quite the same situation as in the first diagram. And I could have instead changed the slope of the constraint and kept the level curve the same. I would still have the same changed picture, or I could have changed them both. I just wanted to get a picture where instead of these being equal, they're unequal. And of course, I could have done it so that the gradient was pointing this way. I would have rotated the level curve a little that way. So now we can indeed see that here, unlike the first picture, it's no longer the case that x hat is a solution, because now I have a point here, and I will call that point x tilde. And you can see that the level, because f is increasing this way, and it's strictly quasi-concave, this has to be on a higher, I'm not going to draw the level curve through here, but you can see that it's on a higher level curve than the level curve for f. So I actually want to be assuming here that let's also assume, I'm going to put this over here as well, gradient f, let's say at x, is never the 0 vector. Right, so f really is increasing in this direction. And so this is a point at which f of x tilde is strictly bigger than f at x hat. And of course, that means that x hat is not a maximizer of f subject to g of x equals b. And in particular, I want to, and in fact, let me just put this in a different color to highlight it. So I want to highlight this and this. That the difference between the two situations is that I don't have a tangency between the level curve of f and the constraint here. In fact, I have a little, what we could call a kind of lens-shaped region here, this region down here, and we actually refer to this as a lens. It looks a little bit like a lens, and we have that the constraint and the level curve are not tangent at x hat down here, okay? Here we had tangency, and there isn't such a lens. The lens is created exactly by the fact that the level curve for f isn't tangent here. So there's a lens on this side, or if I'd swung it the other way, there would have been a lens on this side. So in the case where x hat's not a maximum, I have this lens, I have no tangency. So here, let's put, there's also no lens. And let's kind of characterize the difference between the two in another way. Let's note that up here, I have, since gradient f equals lambda gradient g, I have gradient g dot delta x equals 0 if and only if gradient f dot delta x equals 0. And what that's telling me is if I make delta x's that move along the constraint so that gradient g delta x is 0, then it's got to be the case that gradient f delta x is 0 too, so that I can't increase f. I can't get a positive change in f, because this approximates, of course, the change in f. And down here, I have gradient f unequal to lambda gradient g. Therefore, there actually exist delta x's such that gradient g dot delta x is 0, and at the same time, gradient f delta x is positive. And what that's telling me is, here I can find delta x's. I can move along the constraint, but I can move along the constraint in such a way as to find some movement that actually increases f. This says that gradient f delta x is positive, but that's an approximation to the actual value of f, so I can actually increase the value of f, and we can see that we can do that right there. So that's a sort of complete story of the geometry of constrained maximization in the special case of only two variables. I want to do it for n, and only one constraint, and the constraint is linear. So far it's still pretty special. So there's two ways in particular. Increasing it to a larger dimensional space is it's kind of a big deal, and it becomes harder to picture. But analytically, that's not going to be really an issue. But there's two places where it really, well, actually I could say, I guess, maybe three, at least two places where we need to generalize this. One is that I want to be able to do this the same ideas for constraints that are not linear, And I want to be able to do this for constraints that aren't equations, but are inequality constraints, because in economics, we much more often see inequality constraints than we do equation constraints, I would say. So we want to be able to do, and we want to be able to do more constraints. So three, I thought there were three things. Three things we want to do here. We want to look at nonlinear constraints, we want to look at inequality constraints, and we want to look at the situation with more constraints than just one. And we want to do all three of those today. So first, let's look at the situation with nonlinear constraint. That one is basically sort of easy. I can do it on the same diagrams here. So let's suppose that G is now not a linear constraint. It's nonlinear, and I'm going to draw it quasi-convex. So let's just say that it looks like this. So now the G of x equals B now refers to the level curve of G. Of course, this was the level curve of G when it was linear, but now the level curve of G is over here, so this refers to this, not to this. But the gradient of G dot delta x equals 0 still refers to the line that is tangent to the actual function G at delta x equals 0 vector, at x hat. So it's clear in this picture that if now the constraint is this pink constraint, nonlinear, and for the moment, put the straight line out of your mind for just a moment. I've got my pink constraint, I've got my green level curve of the f function, and it's completely clear geometrically that it's still the case that x hat is, in fact, the unique maximizer of f subject to g of x equals b, subject to being on the pink constraint. All the other points on the pink constraint give me a smaller value of f. So I'm still, I still have x hat as a solution, as a maximizer. And notice as well that even if I didn't have the orange line in there, it would still be the case that the gradient of g for my new nonlinear g, the gradient still has to be orthogonal to, perpendicular to g, and it's going to be pointing this way if g is quasi-convex. If g is quasi-concave, it actually is going to be pointing this way. So g could be increasing here, could be increasing here. It doesn't matter. I'm only interested in the points, the vectors that are on the constraint, where g of x is actually equal to b, where g of x is equal to b. So this picture is still the right picture. It's still the case that x hat maximizes f subject to g of x equals b, and it's still the case that the gradient of f is a multiple of the gradient of g, whether it's a positive multiple or a negative multiple. And so same picture, same story, everything the same. It's helpful to have the tangent, the mutual tangent line. Don't have to have it, but it's helpful. That's, of course, telling me what the delta x's are that do this. So the line here, of course, is the level curve of the first degree linear Taylor approximation to G, and it's also the first degree Taylor approximation, the linear Taylor approximation to F. So it's helpful to have the line here, and the line does show me all the delta x's that have delta x, gradient G times delta x equals 0. So it's still the case that we have this satisfied, and it is still the case that because of this, the delta x's that satisfy gradient G dot delta x equals 0 are exactly the delta x's that satisfy gradient F dot delta x equals 0, differ only by lambda, a multiple. And so again, it's the case that I can't find any delta x that satisfies the constraint or approximately satisfies the constraint on the Taylor approximation that will increase f. So basically, the story with the nonlinear constraint is captured by the first case with the linear constraint, so long as the linear constraint is the appropriate approximation to the nonlinear constraint. And of course, this depends on the constraint having the right curvature properties in some sense. It doesn't have to be that way globally. This could be a local picture. This could be a magnifying glass. So this could be a very, very small neighborhood of x hat where this is happening. And outside the neighborhood, these things could look different. And then, of course, I would only have a local maximum at x hat, and I wouldn't know what happens elsewhere. But of course, if f is strictly quasi-concave everywhere, and g is quasi-convex everywhere in the space, then this is actually going to then have to be a global maximum, as we have already seen. What about down here in the case where the gradient f is not equal to, not a multiple of the gradient of g? Well, down here, I'm going to do the same thing. So what I want to do is I want to have my g nonlinear constraint function g of x. I want to still have it be tangent to my line here. So I'm going to have it looking like this. Again, so this is now, so the constraint part of this picture is supposed to be exactly the same as the constraint part of this picture up here. As I said, I could have actually drawn them on the same picture and done nothing but rotated the level curve of f here. But I think it's useful to have them both on the screen here. And so again, here you can see that, well, this x tilde actually is no longer, does no longer satisfy the constraint, but it approximately does. Now I have that there is, and let me make this one in pink, there is clearly over here, I have, now this x tilde is no longer good, but this x tilde is now such that f of x tilde is greater than f of x. And this x tilde satisfies my new constraint, g of x equals b, where I've made it nonlinear. And the fact that I can do this is still guaranteed by this down here. Because gradient f is not equal to a multiple of the gradient of g, I can indeed find a delta x such that gradient g delta x is still 0. That would be this x here, x tilde. And gradient f delta x is positive, which is still true here. And this is an approximation to what happens on my actual g. So the fact that this is true, I can still find a vector x on the constraint g for this is approximately true, and this is true over here. And I believe there was one more thing that I wanted to say about this. Well, that one more thing that I was going to say, it kind of escapes me right now, so maybe we'll come back and see it a little bit later in the lecture. Okay, so we've kind of completed the story for one constraint, two variables, two decision variables, and actually I'm going to use n, as we said, for the number of decision variables. So we've looked at the case n equals 2, and I'm going to be using m for the number of constraints. And so this would be the case where m is 1 because I only have one constraint. And we've looked at the situation with the constraint linear and with the constraint nonlinear. And now we have two more items on our program here. One is we want to see what happens if we have more than one constraint, and we want to see what happens if the constraint or constraints are inequality constraints instead of equations. So let's do the first thing, which is to say, what happens if there's more than one constraint? Well, suppose I'm still in R2. N is still 2. but now I have, let's say, 2 constraints. Let's change this to a 2. Maybe I should have made this orange since I'm using orange for the constraints, or pink. So let's actually look at a couple of orange constraints here. And so let's go down here, and let's suppose this is one of the constraints. And so now I have to number the constraints. And I've put a superscript on the function g because I'm going to use subscripts for something else. And I'm not sure I'll actually get around to doing that in this lecture, but I'm going to continue to use capital G's for these constraint functions. And eventually I'm definitely going to be using subscripts for something else. And so let me even use another color for a second constraint. So here's a second constraint, and this is g2 of x equals some number b2. Now, I want to find out whether, I want to see if I can find an x hat that satisfies both constraints and maximizes f subject to those constraints. Well, how many different points are there that satisfy both constraints? 1. That one right there. So that x hat satisfies both constraints, but that's the only point that satisfies both constraints. So if I want to maximize my function subject to satisfying both constraints, well, that's easy. X hat's the only thing that satisfies it, so of course it maximizes it, minimizes it too. It's the only possible point. So this is completely uninteresting and, more to the point for us, not instructive at all, except to observe what I just said, that with 2 constraints in R2, we are only going to have one possible point that satisfies both constraints, so long as the constraints are linearly independent. If the 2 constraints coincide and are only one constraint, well, we're back in the one constraint case. If they're parallel, then there wouldn't be anything that satisfies them. So this 2 constraints, 2 variables is completely uninteresting, not instructive in the case of equation constraints. Now, if we had inequality constraints, that'll be different, and we're going to see that in a few moments. But right now, that's not interesting. So the only way it's going to be interesting to have more than one constraint, let's say 2 constraints, and have kind of an interesting problem, is that the number of variables is going to have to be more than 2. We're going to have to be in 3 space. So that's what we're going to do next, and we're going to have to take all this off because we're going to need this to draw our 3-dimensional 3-space pictures. So that's where we're going next, and so we'll take this off, and then we'll be there.